Hello, my name is JewooJun and my student number is 20244082. For this assignment, I have chosen set 4, which is based on cross-validation and Bootstrap. The outline of my presentation is as follows. In this chapter, we discuss two important resampling methods, cross-validation and Bootstrap. These methods do not train the model just once. Instead, they repeatedly draw multiple samples from the training data and repeat the model several times. By doing so, we can estimate how well the model will generalize to unseen data and also assess the uncertainty in our parameter estimates. The main goals of these resampling methods are to estimate the test set prediction error and to evaluate the standard deviation and bias of the parameter estimates. These methods allow us to diagnose the stability and generalization performance of a model trained on limited data. Here, we compare training error and test error. Test error is the average error the model makes on the training data. In other words, how well the model fits the data it has already seen. Test error, on the other hand, is the average error on new, unseen data, which tells us how well the model generalizes to future observations. Training error is easy to compute, but it usually underestimates the true prediction error. As the model becomes more complexity, for example, when overfitting occurs, the training error decreases while the test error increases. The validation set approach is a simple and intuitive method for estimating the test error. We randomly split the available data into two parts, a training set for fitting the model and a validation set for evaluating its performance. The procedure is as follows. Fit the model using the training set. Use the fitted model to make predictions on the validation set. Compare the predicted and true values to compute the validation error. For regression problems, we usually use mean squared error, and for classification problems, we use the misclassification rate. This validation error serves as an estimate of the true test error, which tells us how well the model will generalize to unseen data. Although the validation set approach is simple and intuitive, it also has several drawbacks. First, it has high variance. Because the split between training and validation sets is random, the estimated error can vary a lot depending on how the data are divided. Second, it leads to data efficiency. Only part of the data is used for training, so the model doesn't learn from or available information. Finally, it needs to overestimate the true test error. Since the model is trained on a smaller dataset and performs slightly worse than a model trained on the full data. In other words, the validation error is a bit biased upward. K-fold cross-validation is one of the most widely used methods for estimating the test error. We divide the entire dataset into k equal size parts called folds. Then we repeat the process k times. Each, each time one fold serves as the validation set, and the remaining k-1 folds are used for training. We compute the prediction error for each fold, usually using MSE for regression or misclassification rate for classification, and then take the average of these k errors. Let's look at how the cross-validation error is formally defined. We divide the dataset into k folds and let each fold be denoted by ck. The number of samples in each fold is nk. For each fold, we calculate the mean squared error as follows: MSEK. then the overall k-fold cross-validation error is weighted average of these k errors, CVK. In other words, we combine the validation errors from all folds to get one final estimate. When k equal n, meaning each observation is used as its own validation set once. This special case is called leave one out cross-validation. ROOCV is a special case of k-fold cross-validation where k equals n. That means each observation is used as the validation point once, and the model is trained on the remaining n-1 samples each time. So in total, we repeat this process n times. It is a very intuitive approach, but it seems computationally expensive because we would need to fit n separate models. However, in the case of the linear regression, there is a remarkable shortcut. The LOOCV error can be computed using the following formula CVN. Here, y I hat is the fitted value from the model trained on the entire dataset, and hi is the ith diagonal elements of the hat matrix, which represents the average of each observation. A large HI means that point has a strong influence on the fitted model. So, surprisingly, we can compute the ROOCV error without retraining the model n times, just using this single formula. Now, let's look at the advantages and disadvantages of ROCV. The main advantage is that it makes full use of the data. Almost every observation is used for training. So there is very little data waste and the bias is small. However, the disadvantages are that it requires heavy computation since the model must be trained n times and it has high variance because the training sets in each fold are almost identical and therefore highly correlated. For this reason, in practice, we usually choose k equal 5 or k equal 10. Now that we've used cross-validation to estimate the test error, let's move on to another powerful tool, the Bootstrap. While cross-validation focuses on evaluating a model's prediction performance, the Bootstrap is used to quantify the uncertainty in parameter estimation. The idea is simple. We resample the data with replacements to create many new data sets called Bootstrap samples. For each Bootstrap sample, we refit the model and recalculate the estimate. For example, the mean, regression coefficient, variance, or prediction error. By repeating this process many times, we can estimate the standard error and even construct confidence intervals for any static of interest. In this simple example, we have two random variables x and y representing returns of two assets. We invest a proportion alpha in x and 1 minus alpha in y. The goal is to find the alpha that minimizes the variance of total return R. By expanding the variance formula and taking the derivative with respect to alpha, we get the optimal value alpha. In reality, we don't know the true variance and covariance, so we estimate them from the sample data and compute. Now, let's move on to solving the given problem. The problem is as follows, and we'll solve it step by step. In this code, I loaded the default dataset and used income and balance as predictors. Then I fitted the logistic regression model using the logit function in stats models. From the result, both income and balance are statistically significant. The coefficient for balance is much larger, so balance has a strong impact on the probability of default. The pseudo R squared is about 0.446. In part B, uh, I used the validation set approach to estimate the test error. First, I split the data into two equal parts, a training set and a validation set. Each set contains 5,000 observations, so half of the data is used for training and the other half for validation. Next, I fit the logic regression using only the training set. Both balance and income are significant with a much larger effect for balance. The pseudo R squared is about 0.477. In this step, I used the trained logistic model to predict the probability of default for each observation in the validation set. Then I classified each individual as a default if the predict probability was greater than 0.5. As a result, the model predicts 82 defaults and 4,918 non-defaults out of 5,000 validation observations. Here I calculated the validation set error, which is the fraction of observations that were misclassified. In the code, I simply compare the predict labels with the true values and took the mean of the mismatches. The validation error is 0.025, meaning the model misclassified about 2.5% of the validation data. In part C, I repeat the validation process 3 times using different random splits of the data. Each time, I trained the logistic regression on half of the data and calculated the validation error on the other half. The three error rates were 0.0248, 0.0248, and 0.0238, with an average of about 0.0245. The results are very consistent, showing that the model's performance is stable across different random splits. In part D, I added a dummy variable for student status to the logistic regression model along with income and balance. Using the validation set approach with 3 random splits, I calculated the validation errors as 0.0262, 0.0254, and 0.0252, giving an average error of about 0.0256. Compared to the previous model's mean error of 0.0245, including the student variable did not reduce the test error. So the student feature does not improve model performance. This is the end of my presentation. Thank you for your time and attention.